All right, this video right here is on bond energies. Again, this is a different way to calculate delta H. Dealing with bond energies, first of all, we need to talk about one thing conceptually. In any time that I want to break a bond, so breaking bonds, that is in my reactant side. Anytime I want to break a bond, that is an endothermic process. The reason why is you have to overcome the attractions that you have between those shared electrons. So, one thing to remember this by is whenever I say we're breaking bonds, it takes energy to break. It takes energy to break. We have an endothermic process. Whenever I am forming bonds, that is an exothermic process. Now, when I form bonds, that is in my product side. So forming bonds is exothermic. The reason why is because your atoms have greater energy than the bonds themselves. So you're actually going to a lower energy state whenever you do form a bond. And since you're going to a lower energy state, that energy has to go somewhere, so it's going to be released to the surroundings. So breaking bonds in the reactant side is an endothermic process. Forming bonds in the product side, that is an exothermic process. Now, to figure out if the overall reaction is endothermic or exothermic, it's like, hey, does it take more energy to break the bonds as a reactant than I get out as my product? Or am I getting way more energy out as a product being released than I have to put in as a reactant? So it's basically whichever is greater is going to dictate whether or not that overall reaction is equal to my exothermic or endothermic process. So when we are dealing with bond energies and we can figure out the delta H of the reaction, we've got to say, what is the sum of my bond energies broken? What is the sum of my bond energies formed? Remember, broken is in the reactant side, and bond energies formed, that's in my product side. If you notice that this is the equation that is opposite of Hess's law. Hess's law is the sum of delta H of formations from my products minus the sum of delta H formation of my reactants. Notice how, first of all, this isn't dealing with delta H of formations, it's dealing with bond energies, but this reaction this equation is reactants minus products. Now, this equation right here, Hess's law, that is on your equation sheet. Your bond energies equation is not. So, one trick that I like to think of when I'm dealing with bond energies, BE, that stands for backwards, the B, equation, the E. So bond energies backwards equation. What that's just telling me is just a trigger to remember that if I know Hess's law, I know bond energies is the backwards equation. So it's dealing with reactants minus products. So that might be something to help you a little bit. So when we're working with the delta H of reaction equals the sum of bond energies of my reactants minus the sum of the energies of my products, bond energies broken reactants, bond energies formed my products. The biggest thing that students have trouble with is they neglect to sketch out these bonds. You see the type of information that we have here. We have bond types and bond energies. So these bond energies are what I'm going to plug into here. Now again, this is a bond energy for 1 mole of HH bond. This is for 1 mole of FF bond. So when I'm looking at these reactions, I might have more than one HH bond. I might have more than one FF bond. I might have more than one HF bond. So I have to be able to count those bonds to figure out how many total that I have there. If I have 2 HH bonds, then guess what? I have to multiply this bond energy by 2. If I have 6 HH bonds, then I have to multiply that bond energy by 6. So make sure you pay attention to that. And the way you're not going to make stupid mistakes for this is for being able to sketch out these bonds. Now, the only problem with this is that we haven't gone over Lewis structures yet in this class. So I'm going to give you kind of just like a Band-Aid to slap it on, just to kind of remember for right now, a little bit of memorization. And then when we get to Lewis structures later on in the class, this will make a lot more sense on how I exactly sketch out these bonds and why. So let's start with H2, right? H2 is just going to be a hydrogen with another hydrogen. It's just a single bond there, very simple, okay? The reason why this is the case is because hydrogen only technically needs 2 electrons, and so it's totally happy sharing the 2 electrons that are in that bond right there. F2 is going to look like this. It's just going to be a fluorine with another fluorine. Now you might be asking yourselves, well, I remember from pre-AP chemistry or whatnot that each element has to have an octet, and an octet means that it has to have 8 electrons surrounding itself. Well, yes, that is true. What we're worried about is not the electrons here, though. We're worried about just the bonds that fluorine has. Technically, what this structure looks like is you have 1, 2, 3, 4, 5, 6 valence electrons there. 1, 2, 3, 4, 5, 6 valence electrons there. And then the 2 electrons from the bond is making each fluorine happy. So yes, these fluorines do have a full octet. Now, when you're sketching out these bonds, you do not have to worry about the technical Lewis structure because they're not grading you on the Lewis structure unless it says draw the Lewis structure for F2. So all we're focusing on is this bond and how many of those bonds that we have. So now let's look at HF. HF is going to look like this. H bonded to a fluorine. Now notice that there is a 2 coefficient right there. So what that means is that there are 2 of these structures. This is why I like to sketch out these bonds, because you might say, oh, well, there's an HF there. Let me just say HF is 565. But there's actually 2 of these structures. So it's going to be 2 HF bonds that I have present there. So I'm going to have to multiply this bond energy right here by 2 when I plug it into my equation. So now that I have my bonds sketched out, I get to calculate my delta H of the reaction. So delta H of the reaction is equal to the sum of my reactants, bond energies, minus the sum of my products, bond energies. So my reactants are right here. I have 1 HH bond, so that's 432. I have 1 FF bond, which is 154. And then minus my products. So my products, I actually have 2 HF bonds. So it's going to be 2 times 565. So now, once I plug in everything correctly, all I have to do is the math. So I take this overall quantity minus this overall quantity. And from there, you should get delta H of the reaction is equal to negative 544 kilojoules per mole reaction. Again, just like I've said before, make sure you always put your units down because they might not give you your point if you don't have the correct units involved. So the delta H of this overall reaction is equal to negative 544 kilojoules per mole reaction. So this overall reaction is exothermic because of the negative delta H sign. Something that I've also seen asked before, since this is negative, they say, well, what is favored? Is my bond energies broken being favored, or is my bond energies formed being favored? We'll see how this is reactants minus products, right? What this is telling me is that more energy is being released as the product than I have to put in as the reactant. So I'm getting an overall net release of energy. So therefore, the bond energies of my products are favored in this particular reaction because this reaction is exothermic. If this reaction was endothermic, This would be a positive quantity, so that would be meaning that more energy would have to be put in to break those bonds than I would be getting out as my product. So therefore, the bond energies broken, the bond energies from our reactants would have been favored in that case. Now, I want to show you some other things. Remember how I said I'm going to give you a quick band-aid on how to draw these structures. There are a few things that you'll have to memorize because you won't be able to draw these bond types very correctly unless you kind of memorize this for now. So, quick band-aid. Anytime you see O2, oxygen actually has a double bond with itself. Now, it's important to know if things have double or triple or single bonds because the bond energy of this double bond would be different than a bond energy of just a single bond. And also, it'll be different from a triple bond that we have there. The reason why is because more energy has to be put in to break a double bond than a single bond. Same thing goes for more energy would have to be put in to break a triple bond than a double bond. So oxygen, whenever you see O2, that is a double bond. Nitrogen, whenever you see N2, this is actually a triple bond. Now again, we will understand technically why when we get to Lewis structures later on in the year. Another thing you have to pay attention to is carbon. Carbon can actually get a multiple bond as well, either a double or a triple bond. But the main thing to remember is that carbon always needs 4 things attached. Okay? Always make sure carbon has 4 things attached. Let me give you an example. So I'm going to erase this here, and I'll give you a couple of carbon structures that you might see. So the first one is C2H6. The second one is C2H4. And let's say that the last one is C2H2. So we have to be able to draw these structures and count the different types of bonds that we have there so we can calculate this delta H of the reaction. So C2H6, what that's going to look like. When you see more than one carbon there, you're always going to stick the carbons together. So there's going to be a carbon attached to another carbon here. The next thing that you do is you distribute these hydrogens evenly to each carbon. So since there's 6 hydrogens present, I'm going to distribute 3 hydrogens to each carbon. So there's 1 hydrogen, 2 hydrogens, 3 hydrogens to this carbon, and I'm going to do the same thing for this carbon. So there's 1 hydrogen, 2 hydrogens, 3 hydrogens. All right, so I took care of the 2 carbons, that's there. I took care of the 6 hydrogens, that's there. Now I have to go back and make sure that carbon's happy, okay? Carbon likes to have 4 things attached. So if I look at this central carbon here, there's 1, 2, 3, 4 things attached. So that carbon right there is happy. This carbon here, there's 1, 2, 3, 4 carbons attached. So that carbon is happy as well. So what this is telling me is that this is the correct structure for C2H6. Now let's also pay attention to how many bonds and what different types of bonds that we have present here. So let me get this yellow marker here. Notice how I have 1, 2, 3, 4, 5, 6 CH bonds there. So 6 CH bonds. So what I'm going to do, if I had a CH bond type, I would multiply that bond energy by 6. But notice how we also have one other thing here. We have 1 carbon-carbon bond as well. So we have 1 carbon-carbon single bond that's present there. So I would take 6 times this bond energy plus 1 times this bond energy when I'm adding up my bond energies of either my products or reactants. So let's also look at C2H4. If I want to draw that structure, I put my carbons together. So there's a C and another C. Then I distribute these hydrogens evenly. So I have one hydrogen here, two hydrogens here, and I'm just drawing this the way I'm drawing it just because I know that's what it looks like. You don't have to worry about the direction you draw them for now, just that you draw them there. So notice how I have 4 hydrogens total, so that's good. 2 carbons total, that's good. Now you've got to make sure carbon's happy. Remember, carbon has to have 4 things attached. Well, this carbon here only has 1, 2, 3 things attached. This carbon also only has 1, 2, 3 things attached. So what I'm going to do to make both of these carbons happy is I'm going to put another bond right there. That's okay because carbon attached to another carbon can get multiple bonds like this oxygen and nitrogen here. So now if I look at this carbon, it's 1, 2, 3, 4 things. This carbon is 1, 2, 3, 4 things attached. So that makes both of the carbons happy. Therefore, this is a correct structure. Now let's talk about what type of bonds we have here. We have 1, 2, 3, 4 CH bonds, and we have 1 CC double bond. The energy for a double bond will be different from the energy of a single bond, so we have to pay attention to that. Now let's look at our last structure, C2H2. So this was C with another C, so that takes care of that. H2, we're going to distribute both of the hydrogens evenly. So I'm going to put a hydrogen on this one and a hydrogen on this one. So I have my base structure. I have 2 hydrogens. I have 2 carbons. This carbon and this carbon is not happy because there's only 2 things attached to either one of those. So what I'm going to do to make it happy is give it 2 more bonds. So now this carbon has 1, 2, 3, 4 things attached, and this carbon has 1, 2, 3, 4 things attached as well. We have to make sure we uphold the 4 things attached. The reason why is because this fulfills the octet of carbon. Now, how many different bonds do I have of everything? Well, I have 1, 2 CH bonds, and I have 1 CC triple bond. So then I would plug that into my information as well. Okay, so I hope that helps a little bit. You will get more practice sketching out these bonds when you're working on practice problems in class. So hopefully this is a good little band-aid to kind of help you with this until it makes total sense when we get to Lewis structures later on in the year.